Thank you for inviting me to speak here. As Pete mentioned, we increasingly have applications that are looking at cloud computing technologies to run. And why does it happen, and why does it happen increasingly? So one phenomenon that we're seeing is a rapid expansion of experimental sciences. So at Argonne, we've got this advanced photon source, which is a fantastic experimental instrument generating a lot of data. We are working with scientists from APS right now, trying to provide on-demand virtualized cycles for them in the Lab Computing Resource Center. So there was a big request from them. They were saying we need more computational backups for our calculations that support experiments, that support ongoing experiments, so they need on-demand response. But it's not just LCRC that is having this demand. The experimental sciences are expanding, and they're expanding because there's more data available now, because we are able to instrument oceans, rivers, forests, cities, what have you, turning our planet into a sort of planetary scale instrument with those different sensing technologies. We also get data from social networks and from citizen science. I work with geographers at NCSA, for example, who collect geospatial data from various different sources, and then they process that data on demand in order to get a dynamic picture of how different areas evolve, right? So I've got here a picture from the Array of Things at University of Chicago's an NSF-funded project at University of Chicago that instruments the city of Chicago with sensors that produce interesting data. Another thing that is also happening is that many people are saying, in order to better work with my experiment, I need to run simulation because I want to predict what will happen depending on how I configure the next iteration of my experiment. So General Electric's pioneered this digital twin model where you collect data from sensors, then you run a simulation to see what happens, and then you compare that with the data from sensors, and then you can converge on predicting how you're on the wear and tear, for example, of your various electronic components. People in science want to leverage that digital twin model for experimentation as well. Another thing that is happening is the end of Moore's law. So people who are buying clusters to run analytics computations for their experiments, all of a sudden are finding that when they buy the next cluster, it's no longer keeping up with their computational demand, which it used to do, thanks to Moore's law, right? Now it's no longer keeping up, so they are looking to supercomputers to now support those analytics on-demand computations. And then finally, a model that is gaining popularity is making computer an instrument. So people are building models, they're running it on the computer, and different research group can schedule time to work on that model deployed on a supercomputer and inject different conditions into that model. So this is an experiment via simulation, and that's gaining popularity. So in short, many groups are now seeing increased need for on-demand computation, and also increased need for controlled computational environment. Because if you're trying to run on demand and somebody says, sorry, your code doesn't work anymore because we had to upgrade the operating system and now various things changed, that of course not on demand anymore. So I will, in this talk, focus on controlled environments because we had Docker and virtualization in the title. If there is a little bit of time, which there might not be, I will also say a few words about on-demand and how we handle that. But for now, the focus is appliances. Appliances, you know, intuitively, virtual machines are appliances, Docker containers are appliances. It's just one word that describes the various containers that we use on machines. So I'll talk about pros and cons, about different implementations, and then I will talk about a case study comparing KVM and Docker side by side that was performed by scientists in my group. So first of all, what are appliances? As abstraction, if you think about it, appliances are just simply application plus the environment that your application needs in order to run. So what happens here is that we decouple the hardware from the configuration that resides on that hardware, right? In the high-performance computing world, we all got used to when we come to a resource, it's a resource that it's a certain hardware, but it's also configured with certain operating system and applications and libraries and tools on it. What we're doing with appliances is we're taking this notion of environment, making it separate from the hardware, so that if you're looking for, let's say, a high memory cluster that is configured with CentOS, and what you have is high memory cluster that's configured with Ubuntu, and low memory cluster that's configured with CentOS, you have a problem, right? But if you split the environment from the resource, you can mix and match. So the benefits of using appliances that most people are struck by is you have control over the environment, so control over the environment in which your application is executing. Many people like to use that for managing versions and managing reproducibility, so that if you run your application today and then you need to come back 6 months from now and rerun it in the same exact environment, you can actually do that, right? You have control over the environment, and it's not that certain aspects of that environment were upgraded. In the meantime, your application is not returning the same results and you don't know why. So reproducibility is a big part of the push towards working with appliances. It's also a practical way of packaging your application, right? It's not that somebody has to follow long stream of instructions in order to get it set up. It's that they can essentially with one command run and have it deployed on the machine. Some people like the live migration and sharing that comes with appliances. You can snapshot an appliance, somebody else redeploys it, and they have access to the memory that came with your appliance in the case of virtual machines, and all of the factors. And then finally, resource providers like looking appliances because they frequently have to reconcile requirements coming from different application groups that are sometimes conflicting, right? So you don't know if you should configure a resource this way or that way, and maybe you have to change it from time to time and adjust it and tweak it. There's a lot of time that goes into that. If everybody has their appliance, you don't have to do that. But there are also challenges of using those appliances, and challenge number one is really the same as the pro that you have on top of that, right? So you can control your environment, but you also have to control your environment, right? So all the operating system upgrades and security upgrades and all of that stuff that was taken care of you by your friendly system administrator, now you have to do yourself, right? And some people don't like it, so they would like to have control over it, but not necessarily all the maintenance baggage that it brings. There are security implications. Every time we introduce another layer to the system, right, it's possibly a layer that could be attacked in some way, and we need to learn about new attacks. And finally, there is the performance issue. Again, we introduce a layer that brings with it a certain overhead. So what I'm going to talk about is appliance implementations, because they offer various different trade-offs in that space of the different challenges that I outlined here. So there are very many appliance implementations, and you can see the logos for many of them. I would like to call out a few specific ones. Zen and KVM are virtual machines. Zen is a virtual machine that is being used by Amazon Web Services. So if somebody runs on Amazon, they are going to use a Zen virtual machine. KVM virtual machine is remarkable because it has been implemented in the Linux kernel, so you don't have to deploy anything special. If you have a Linux installation, relatively recent one, you can use KVM. Palacios is a lightweight virtualization technology that was developed originally at Northwestern. Nowadays, it's part of a collaboration that develops very lightweight virtualization methods. They ran tests on Sandia Storm in the thousands of nodes and found very little overhead, very good performance for that. And then there are container technologies. The most famous one is Docker, and I'll go into the difference between virtualization and containers later on. So the most famous one is Docker. There's also Lexi and LexD, which are similar to Docker in that they are containers, but they try to provide more features. And there's also Shifter, which is an adaptation of Docker specifically that was developed at Lawrence Berkeley National Lab that seeks to get around some of the security limitations that come with Docker. So they make sure that, for example, no bad directories are mounted, that everything can be managed and so forth. So those different implementations differ by image types. They could be virtual machines, they could be containers. You could also have bare metal images, and in fact, that is what we support on Chameleon, and about that later. They can differ by provider, so each provider has certain conventions on how to deploy virtual machines, for example. And that means that Amazon image won't always work on some other test bed on a, let's say, OpenStack installation. It's sort of, if you configure the image carefully, it could work. And then there's also something to understand, which is contextualization. So if you want to deploy virtual cluster, there's certain information that becomes available only at the time of deployment. For example, the IP addresses that your virtual machine gets, they become available only on deployment, or security information may be generated only on deployment. In order to configure a cluster, that information needs to be exchanged between the different instances of virtual machines, and technology that orchestrates that exchange is called contextualization. Very quickly, there are ways of managing virtual machines and container images that allow you to generate different types, different implementations of the environment that you need consistently. So rather than, let's say, you're working with an image on Amazon, you make a bunch of modifications, then you snapshot, right? If you go back and if you make changes to your installation, you can generate an Amazon image, your friendly local OpenStack installation image, and so forth consistently, so they all represent the same environment. And so, for example, on the Chameleon testbed, we use OpenStack Image Builder for that. There's also technology called Packer, which simply does the installation process for you in a consistent manner. So that streamlines the image management, so that becomes less of a problem for users who just simply want the control over the environment, want to run. So what we have done in my group at some point, we said, well, let's compare two technologies, KVM as a representative of virtual machines, and Docker as a representative of containers, and see how the overhead of those two compares. So a few words about why there would be a difference. So one reason why there would be a difference is that the way virtual machines are implemented is they present a virtual hardware to what's called the guest operating system. The guest operating system is a system that you install in the virtual machine, right? So typically, either there is an overlay, some small overlay on top of the operating system. So for example, in Zen, you deploy something called Virtual Machine Monitor. In Zen is actually called Hypervisor because it's a paravirtualization technology. In KVM, like I said, it's part of the Linux kernel, so we drew it here as part of this operating system, the host operating system, right? So it's either part of the operating system or something deploys on top of operating system called Virtual Machine Monitor, and it's a piece of software that allows you to deploy virtual machines and terminate them, right? Once you have virtual machine deployed, you can install an operating system inside that virtual machine or change that operating system, and then of course, on top of that guest OS, you can install whatever libraries and applications you want to do. In containers, things are much simpler. So there is no virtual hardware that gets generated for you. What Docker and other containers do is they take namespaces they use namespaces to provide isolation between users' processes, inter-process communication, mount points, and so forth, right? So by use of those namespaces, it looks like you only see your own processes, you don't see other person processes. The other thing that they also use is control groups, which manage resources on the machine, right? So they make sure that if you have several containers deployed on the machine, nobody takes all of the memory, for example, right? But instead that is divided fairly between those containers, right? So that's really the only thing that they do. And therefore, they are much lighter weight than virtual machines. So the challenge for us was to figure out how much lighter weight. So to sum up the differences here from the user's perspective, if you want to install a different guest OS, then you really want a virtual machine, right? With a virtual machine, you could have your host operating system be Linux, but inside the virtual machine, you can have Windows, right? And it's it's very often deployed in that configuration. If you use containers, if you use Docker, you are using the host operating system, so you can't have your own operating system. You can maybe have different packaging of an operating system, right? But you're using the same kernel as the host operating system. For startup time, virtual machines tend to take a few minutes, and that differs based on how large your image is, how long your boot takes, what's part of the boot process, and so forth. For containers, it takes just a few seconds, because literally the only thing that happens is setting up those namespaces and control groups. Isolation and security, on the other hand, virtual machines are very well isolated. The attack surface is the virtual machine monitor, which is small. For containers, on the other hand, the attack surface is the kernel, the operating system kernel, which is large, right? So there's a lot of opportunity there. Live migration support in virtualization is, of course, available. In containers, not really, although the LXD and LXI implementations are looking at that right now. And is it integrated with OpenStack? OpenStack is the infrastructure as a service implementation. In both cases, it's yes, because both of them are appliance implementation. Appliance is just a building block. So, the way I see the development of the various different virtualization technologies and containerization technologies is really like binary search, right? We start with bare metal, then we say, oh, virtual machines are a very good thing. They provide this isolation, this encapsulation. Oh, but sadly, they are not performing very well. So let's make well-performing virtual machines, right? Let's optimize them. Oh, but that's still not good enough. So let's try on the other side, right? Let's throw out the virtualization. Let's look at containers, right? So we're sort of trying to converge somewhere there in the middle is a good trade-off between the various features that those technologies offer and the performance that they offer. So there's another one called LXD, right, for which has the live migration feature. So we were trying to look at what is the performance comparison between KVM and Docker like in practice, and we ran some experiments. Those were run by Yu Zhu, who was a student in my group, and Balaji Subramaniam, who was a postdoc. And they ran those experiments on a test bed called Chameleon, which I operate. It's a test bed of about 15,000 cores, 5 petabytes of storage that are distributed over University of Chicago and the Texas Advanced Computing Center. The interesting thing about Chameleon is that it's deeply reconfigurable. So in other words, you get access to bare metal. You, of course, get root on those machines. You can reboot. You can power it on, power it off. You get access to console. You can change the BIOS. You can change the firmware. So they are very well suited to the experiments that I'm just going to describe, right? Very importantly, every user of Chameleon gets an isolated, dedicated environment. So you are the only person using those machines. You're not getting traffic or any kind of disruption from somebody else executing on those nodes. And just going back to that, the 600 nodes that we have, it was configured as many of them are in just one homogeneous partition. It was configured like that on purpose to support HPC experiments, right? So 600 nodes is perhaps not HPC, but it's as HPC as we could afford at the time. And one last thing, Chameleon is available to any US-based researcher or their collaborators. So probably anybody in this room can use Chameleon, I would guess. So back to the comparison, comparing KVM and Docker. We started out with micro benchmarks, and we ran LM bench. And so what you see here is the different aspects of the benchmark compared, and they're compared via ratio to bare metal. So the blue one is Docker, the yellow one is KVM, and you see the third number on the y-axis from the bottom is 1. So that's what bare metal gives you, right? And you can see that the slowdown of Docker is with respect to bare metal is relatively modest when compared to the slowdown of KVM, right? So we concluded that KVM has worse performance than Docker, nothing earth-shattering there. It's roughly what we expected since it's a heavier weight technology. So then we started looking at application or application proxies from the Mantivo set of benchmarks. And we looked at Cloverleaf and COMD. They are hydrodynamics and molecular dynamics, represent hydrodynamics, molecular dynamics codes respectively. And the experiments that you see here were performed on one node, but we were increasing the number of threads from 1 to 24. So on x-axis, you've got the number of threads, and then again, a ratio on the y-axis. And again, Docker is blue, KVM is yellow, and you can see that Docker is, in many instances, is essentially the same as bare metal performance. KVM is typically a little bit more. We've got one outlier there with Docker's. Both Docker and KVM seem to be much faster than bare metal. We never managed to track down the specific reason for that, but typically what happens in those instances is that when you insert another layer, that layer caches some memory. So when in virtual machine, for example, when things running in the guest operating system get out of memory, there's still memory cached that is relevant to the virtual machine itself, and that allows it to get better performance. Like I said, we didn't track the specific reason for this one. So then we started looking at scale-out results. In other words, when you add more nodes, what happens? And for those scale-out results, we used the MPI benchmarks for those applications. On the x-axis, we were increasing the number of nodes up to 64 nodes. And these are the results, right? So again, and so this time we didn't compute ratio, but you see this time bare metal is in blue, Docker in yellow, and KVM in red. But you can see that KVM was taking substantially more time, right? Docker being very comparable for the most part with bare metal. But then we said, okay, did we do it right? So did we set up KVM in a fair way for the comparison with Docker? So one aspect of that was setting up PCI pass-through correctly. It turned out that, by default, it was not set up correctly. Exposing the NUMA topology to KVM, right? So it doesn't mix and match the different memory bags, and pinning the vCPUs. And when we have done all these things, all of a sudden, we reran the benchmarks. All of a sudden, we saw that KVM was much better performing, well, not much better performing, but slightly better performing than Docker. So what happened here? Well, so one conclusion to draw from this, that KVM was simply harder to set up correctly. Right? So it's a more complex technology. There are many moving parts. When we did finally get the setup correctly, it actually did not perform too badly. The other thing that to potentially conclude is KVM has been under development for many, many years. Docker has seen relatively recent interest, so there are no doubt still many things to improve in Docker, right? So in general, we recorded here the performance, the results that we have seen, but in general, we would expect better performance from Docker. Many people expect better performance from Docker, but it turns out that when you actually run the benchmarks, at least right now, it's not that different. Does that mean that KVM is better than Docker? Of course not. That means that it's better for this specific setup, for this application, and that probably just simply more studies need to be done. A few words about high-performance networks. One reason why virtual machines are very often get their reputation for bad performance is because they don't use RDMA technologies very efficiently. So those are two slides that I borrowed from DK's Panda group. It's a Zhang and al. CC Grid 2015 paper, where their group does a lot of research on optimizing MPI and also Hadoop in virtual environments for InfiniBand. And so they run different tests from NAS Parallel Benchmark and from Graph 500 with their applications. And they found that in the worst case, the performance difference that they were seeing was less than 10%. So this is the performance over InfiniBand once you use all of their optimizations. Okay, so much about appliances and containers and virtualization, their performance and the various trade-offs. I will just briefly touch on on-demand availability in HPC. So here's the crux of the problem. In the HPC model, people typically schedule on availability, right? They schedule batch computations, in other words, and batch computations are queued up. When resource opens up, the computation is scheduled. And the computations are scheduled in order to generate the best possible utilization, because supercomputing resources are expensive and need to be amortized. In the cloud model, people schedule based on user concerns. In other words, they tend to schedule on demand. But if you schedule on demand, you have to keep part of your resource idle, in case an on-demand request comes, right? Otherwise, you have to reject the request. So that doesn't lead to very good utilization, and hence there's an issue. What we're seeing now with the increased interest in cloud computing is that many resource centers divide up their resources. They run Torque, they run batch computing in various implementations on a part of the resource. Part of the resource is exposed as on demand. So for example, at Argonne, we have a resource called Magellan, which provides on-demand computation. NSF recently funded several on-demand computing-based systems. They're called Comet. There's one called Jetstream at Indiana University. There's Bridges at Pittsburgh Supercomputing Center. There's also Chameleon. Chameleon provides, I already explained, those bare metal nodes, provides them either on demand or advanced reservations. If you want to reserve the whole test bed, for example, you can do that, but you have to let us know in advance. And there are also some hybrid models. So Shifter, for example, not only makes improvements to Docker, but it also allows you to run Docker as part of a batch system. Right? So it also provides a driver for a batch system that allows you to deploy it. So what we're trying to do right now in the Lab Computing Resource Center is merge those two models so that you don't statically partition. You've got your batch computing on this side and your on-demand on that side, but you run them all together, right? And we're trying to see if we can get both high utilization and on-demand availability on the same system. We've done something similar before, and so what we have done before is we just sort of used high throughput computing. So the high throughput computing, small jobs, you can kill them, or you can terminate them, and they will just get rerun by the scheduler. So this is a model that is supported by systems like Boink and Condor, for example. So we figured, well, if we can get enough of those small computations and we can run them around the on-demand computations, then we can get both good utilization and we can get on-demand. And so we implemented that in a system called Nimbus, which is very similar to OpenStack, but it's a research system. And we did some comparison. So you see here a resource where we supported on-demand only. So we had a good on-demand resource, but the average utilization was 36%. And you can see that the resource is essentially cold. When we started filling in the gaps with high throughput computation, that resource started heating up. So our utilization started getting better. And we've got a paper about this. We're trying to use a similar technique in LCRC now, but instead of killing jobs, we're trying to proactively predict when the on-demand requests are going to come and steal some nodes from the batch partition. There are some preliminary results which show that it's a promising approach, essentially. Okay. I would like to get a couple minutes to conclude. So is an interesting tidbit of where we're going from the resource perspective. So back in 2009, somebody published a paper which under the title, "Will Cloud Computing Reach Top 500?" And the answer at that time was no, it won't, right? So that was the conclusion of the paper, and that was also the received wisdom of the times. However, in the following year, in 2010, Amazon Virtual Cluster was put as number 42 on the top 500 list, right? So number 42 is the top 10% of top 500, right? At the same time, around that same time, one of my colleagues did a calculation, and he said that about 10% of top 500 are interesting supercomputing architectures, and the remaining 90% are essentially commodity clusters, very powerful commodity clusters, but commodity clusters which are very suitable cloud technology. So there is a mix of those different capabilities. Appliances are, of course, on the one aspect of cloud computing. I said a few words about on-demand, but there's also the issue of fine-grained resource management, so matching the best resource to your application, right? So if your application needs, let's say, high memory and SSDs and high bandwidth I/O in general, so that you get scheduled on those nodes, not some other nodes. There are various data-focused frameworks like Spark and Hadoop. There is support for generally new patterns of processing. Appliances are just a building block of cloud systems, so whether it's Docker or virtualization, architecturally it fits in the same place in the landscape. So the question is, can OpenStack run with Docker? Of course it can, right? Can Amazon run with Docker? Technically, yes. It's a business question, and security question, and different kind of question whether they want to do that. And we talked about various appliance implementations, and the performance is perhaps better than some people think, but it's clearly requires more work to be conclusive about this. A few things to try if anybody is interested in appliances. First of all, you can go to Chameleon and you could redo our experiments. We already support bare metal images which have Docker and KVM on them, so it's very, very easy to run those experiments. We also have ConnectX 3 InfiniBand if somebody wants to check out how the high-performance networking works in practice. You can try out other technologies in HPC context, so we've got appliances with all sorts of things, Hadoop and Spark and others. You could use some other clouds. You could use some of the NSF clouds that are currently available, Jetstream and Bridges, or Chameleon for that matter. And you can also share your research. So in Chameleon, we've got people who are contributing appliances with their research so that others can run experiments with their tools easily. So for example, we've got contribution from Barcelona Supercomputing Center. If you have technology that could be interesting to other researchers, that's something to consider.